All right. It's 11 o'clock. I guess it's Eric time. Sorry. There's another Eric. Sorry. Okay. You're welcome to come here. So I apologize for that, but hopefully I'll keep you entertained. This was a talk that actually I was telling a few of you at the breaks has actually really kept me awake for many, many hours and many days coming here. So this is the talk that, first of all, I have to apologize if this talk seems rough around the edges. I created everything from scratch for this workshop. So it is the first time I'm showing this, so I hope you'll forgive me if it looks weird. But I did it with a good purpose, and the good purpose is that I was trying to organize a number of thoughts that my students and I have had about the 2D materials literature over the past year or two. And you'll see in a moment what I mean by this. So I should probably just advance things. Okay, so yesterday's tutorial was my perspective on what 2D materials may be good for. So today it's trying to clarify some what I call alternative facts about 2D materials. And I wish the audience had tomatoes and eggs and other things so you can throw them at me in case I say something really bad, because it would be more fun that way. And I might. Again, I apologize. These are new slides, new to me, new to you, but here we go. So, we have a political situation in the US, and some of the words that they use on television are fake news and alternative facts, right? When President Trump doesn't like something, he says it's fake news. When one of his counselors doesn't like something, she says it's alternative facts. So I like the term alternative facts a little bit better. But unfortunately, what I will try to tell you today is that some alternative facts have been propagating about 2D materials as well. And I think some of these, well, this is my definition of alternative fact. A statement or a number that somebody says it's true, even though there's reasonable evidence that it's not, and maybe even, maybe there's some error bars or something like that. So it probably shouldn't be taken as real. My pet peeve is people who report mobility without reporting error bars, without telling you, at what carrier density, at what kind of defect density, all kinds of things. And if you did that correctly, you would find out that actually the mobility is probably a range of values. It's probably not that number that exactly they said. So I have friends who work on organic transistors, and when I told them this, they said, oh, we have that problem in organic electronics. And they sent me this paper. This is written by, I know these two, actually these three, Tom Jackson, Juana Jorquesto, and David Gunlach. This is actually a pretty recent paper. And apparently in organic electronics, people for many, many years were saying that the mobility of organic electronics is less than 1, and then all of a sudden, all these papers started appearing with mobility of 30, 40, 50. And these authors actually say that, wait a second, there's really a problem with the measurements, and it turns out that the mobility measurements that everybody is publishing and getting, Nature papers out of, is actually overestimated by about a factor of 10 or more. So that mobility you read about organic electronics having mobility of 50 is actually probably 5. Even 5 would be a record probably. But there's a lot of papers like that. So we have those papers too, unfortunately, in 2D materials. Okay. So here's who coined the term alternative facts. Her name is Kellyanne Conway. She's the counselor to our 45th president, who, like Voldemort, will not be named. Now, again, my problem is that these things occasionally propagate, like Facebook propagates her alternative facts, and then, people repeat them, and then soon, you have some, shooting in Texas. So those are obviously much more real-world consequences. The consequence in 2D materials is just that my students waste a lot of time pursuing something and then finding out that it was actually an experiment that wasn't correctly done. So for us, it's mostly a waste of time, so I put this together. So we try to clarify a few things. You'll see this list is very incomplete. In fact, I've already talked to a lot of you at the breaks, and I learned that, in everyone's, subdiscipline, obviously there's other things that bother you. So mine will be obviously related to what I do, which is more devices and thermal and contacts and whatnot, maybe a little bit about growth. So if you see something missing, or if I make a mistake, please tell me, right? Just email me at that address, or tell me at the break. Okay, let's get started. So I've got 20, I think I've got about 20 of these. So there's a number up there, and I started with number 1. Number 1 is, what are 2D materials, right? And this is my chance to quote Shakespeare. And you know, the thing that bothers me is that sometimes you read, you know, about a really thick 2D material, and somebody says, oh, you know, I have this 2D material, and look at the thick. Okay. I'll try not to touch anything. Then you look at the thickness, and the thickness is, you know, 10 nanometers or something like that. So that led me to talk to a bunch of people. What is a 2D material versus a thin 3D material that maybe is just anisotropic? And so I looked into this, and you know, I'm pretty convinced that physicists agree that two-dimensional electro gases are 2D. Those are different beasts, but they are 2D, right? That's what people call them. And then we have these things, right, which we know that really only the monolayers are really special, usually, right? So I think there's general agreement that monolayers are usually special. Then the question is, you know, what is really 3D anisotropic? And I really tried hard to come up with a number, and today I'll say that anything over 5 layers is actually probably 3D anisotropic. It's not that special. Monolayers are definitely special. Bilayers a little bit special, and then the specialness kind of goes towards 3D, kind of like this. So this is the energy band gap, the computed energy band gap as a function of number of layers, and you can see for a variety of 2D materials, it seems to converge to bulk pretty quickly, and this is where I got the 5 layers from. It's an arbitrary number, so you know, if you think it's 10 layers and I say 5, I think we're fine. Right. Here's another calculation showing, you know, 1 layer looks special, 2 layer looks kind of special, 4 layer and bulk are not that different. And when the difference between the band structure of 4 layer and bulk is less than 1 kT or a few kT for me, you know, it's kind of like they're starting to look like bulk. So I think anything over about 5 layers, I will probably try not to call it 2D. I'll call it layered whatever. Now, there's obviously different things here. The 2D something depends on temperature, depends on the electron, phonon, or photon wavelength. So it depends on what you're actually using it for, right? You know, for example, if you're looking at thermal conductivity effects, you actually need a 1 micron thick MOS2 film to converge to the bulk thermal conductivity. This is actually something we've measured and modeled in my group. This is a recent paper earlier this year. So you know, there's really a size effect in the thermal conductivity, and you don't recover the bulk MOS2 thermal conductivity until you're about a micron thick. But you see this in silicon as well. So this is really a 3D boundary scattering effect. There's some quasi-ballistic phonon transport going on here. And the rest is just basically, you know, boundary scattering. So is that really a 2D effect or is that a 3D effect? I don't, you know, won't take sides. I think it's more of a, well, I will take sides. It's a little bit more of a 3D effect, but, you know, I just want to point that out, that there are, obviously, these depend on what you're referring to. Okay, moving on. This is a very famous picture. This appeared in 2011 in a paper that I will not mention, but a paper that gets a lot of citations. And they got the thickness wrong. And this has been propagating in the literature for eight years now, right? And everybody says the monolayer MOS2 thickness is 6.5 angstroms. And so I actually looked it up. It turns out that we've known the monolayer MOS2 thickness from Linus Pauling in 1923. Yes, this is Linus Pauling, who had 2 Nobel Prizes, one in, I think, chemistry and the other one in peace. He was kind of an accomplished person. And so for 100 years, we've actually known the correct, this is directly from his paper. He measured the MOS2 interlayer spacing, and he found, this is his text, he found that, well, it's 6.15 angstroms. This number came from an AFM measurement. People who do AFM measurements know that, of course, if there's stuff on your tip or stuff on the surface, you can get whatever you want in there. You can get a nanometer in there, right? But I think a lot of people have propagated this number, as the actual true thickness. And it's maybe not a big deal, but for thermal measurements, actually is kind of a big deal, because you have to multiply this by the correct number of layers to get the layer thickness in bulk. And by the way, this is a recent paper from, I believe this paper from Nature Communications. They intercalate lithium into MOS2, and boy, they put a lot of lithium in MOS2, and they showed that even if you intercalate lithium, you cannot change the lattice spacing much beyond 6.2 angstroms. So it's not 6.5, it's at most 6.2 if you put a ton of lithium in there. Right, and so it kind of bothers me, partly because, in the graphene community, we've agreed a long, long time ago that the graphene thickness is 3.35 angstroms, which is the actual lattice spacing in graphene as well, right? So we've agreed on that for many, many years. In fact, we've agreed on that since Rosalind Franklin's work in 1951, maybe even earlier. But in the MOS2 literature, we seem to be using the wrong number. Not not everyone, obviously, because there's references that are actually getting it right, and some of them are listed down here. And so, I went and, again, I apologize. These numbers are probably not the latest and greatest, but this goes back to a review paper by Wilson and Yoffe from 1969, and these are the recommended lattice parameters from that paper based on the X-ray measurements that were available at the time. But you see, the X-ray measurements actually give you the right number. So I tend to trust these numbers. I believe this is all 2H phase, so this is not 1T prime, it's none of that stuff. And here's where the things really becomes important, because if you're trying to compare the thermal conductivity of a monolayer, bilayer, or bulk, you better get the thickness of bulk when you multiply by n layers. And that's why that actual monolayer thickness, you have to get it right. Otherwise, you're going to not be comparing the right thickness, right? Electrically, I mean, for mobility, it doesn't matter, right? But for thermal comparison, it matters. And we need to be consistent with graphene, graphite, which we have been, the graphene literature is fine. Okay. Number 3, minor stuff. This is like me complaining that, oh, I don't know, the temperature is in Fahrenheit instead of Celsius. It's not a big deal. I can really understand both. But here's, I'll say it anyway, because again, if you go back to Ewan Cardona's book, Dresselhaus's, and even Conyers Herring's work from 1942, the labels for the Brillouin zone, there's actually a convention for these things, and I think we screwed them up somewhere along the way. And, by the way, I've exchanged emails with Marcos Pimenta about this as well. And he explained to me a few of these things, so maybe I'm still getting it wrong, but I'll say what I think is right. If you look at the original group theory papers, that's the gamma point, fine, we all agree. That's the K point, so far so good. The line between them is called the tau line. The tau line, that's a capital T, but it's actually tau because the convention is that, and again, I'm learning this from textbooks. The convention is that the lines inside the Brillouin zone are Greek letters. Inside the Brillouin zone, Greek letters. So that's a capital T for tau, not T, tau. This, by the way, is a capital sigma. Okay. So now there's a really special point along this line, which is that conduction band value right there. And we'll come back to that conduction band value later in this talk. And that is called everything. I've heard it called Q, I, and here I don't care if you call it Lady Gaga, as long as I know what you're talking about, right? The problem is some people occasionally call it sigma, and that's wrong. I'm pretty sure sigma is wrong. Q and I and lambda, I've even seen lambda. I think lambda is maybe okay, although lambda, that seems to go against the convention. Lambda should be for lines because it's and actually there is a lambda line in there, so that's kind of confusing. But I think sigma is incorrect because, first of all, sigma cannot be a point. Remember, a line is a Greek letter. And sigma is actually this line. This is gamma to M. So people use that line notation to refer to that conduction band value, and now my head explodes, and that's not good. So that part is, I'm pretty sure that part is wrong. I think the rest is okay. You can call it Q or I. I don't know where Q or I comes from. I couldn't find it. Professor Marcos Pimenta couldn't tell me. I talked to many people, and I couldn't, Okay. So, band gaps. Oh, I go to so many talks, and the talk starts with, I study MOS2 because it has a great band gap of 1.8 EV in monolayers. Okay. And then I go, okay, I know the photoluminescence and optical absorption give us 1.8 EV, but is that the real band gap? Well, maybe we can debate what's real and what's not, because I'm an electrical engineer, so I worry about electronics more about optoelectronics. But still, I think people make a confusion between the optical band gap and the quasi-particle band gap, which is bigger, right? And this is not my text. This is taken from this paper from Rasmussen. And they say this false conclusion based on a false conclusion is based on a common confusion between the optical and the quasi-particle band gaps, right? To make things worse, if you use DFT calculations, you also get 1.8 EV. But DFT is known to underestimate the band gaps. So again, I've attended talks where people have said, look, my DFT calculation is great because it matches the photoluminescence data. Of course, they're both wrong. I mean, they're both, the photoluminescence data are the data, it's fine, but you're comparing the wrong things, right? I'm not going to bother you with my literature search. My students and I have done probably not an incomplete literature search to find out what the band gap, the recommended band gap is for monolayers on SiO2 at room temperature. But these are the numbers that I came up with. So the selenides have lower band gaps, moly sulfide is there, and tungsten sulfide has slightly higher band gap. If you press me, I'll say the band gap for MOS2 is 2.3 and not 1.8 or 1.9 or whatever. And by the way, the reason, it's written here, but I didn't say it, the reason for the difference in the optical gap and the quasi-particle gap is that the binding energy of excitons is quite large. It's about half an eV or something like that. Okay. So notice I said 2.3 EV for MOS2 on SiO2. There seems to be more and more agreement that the actual band gap of suspended MOS2 is actually even larger, about 2.5 or 2.8 EV or something like that. Please tell me if you have different numbers at the break or, or afterwards. This is very nice calculations done by KJ Cho at UT Dallas. So this shows the band gap calculated with a simple substrate and sandwiched for MOS2. So again, if it's freely suspended, it's about 2.7, 2.8, and then it kind of asymptotes towards, something else due to screening, right? And this, by the way, is the dielectric constant of the substrate. So you see that's where SiO2 is. That's 3.9 dielectric constant. So that gives about 2.3, which is consistent, by the way, with the measurements that I found elsewhere. But now I'm learning further from reading the literature. And these are really nice measurements done by Tony Hines and done by people at Berkeley right now, that actually if you put stuff on top of these TMDs and you have stuff below it, you can actually create these lateral heterojunctions due to screening. So not only is the band gap not just a single number, but it really depends on what the heck you put above or below it, right? So in this case, they put graphene above it, and look, they shrank the band gap by how much? By about 0.15 EV, and that's measurable. That's really measurable. And this really matters for electronics because you're going to end up with extra Schottky barriers at your contacts if this really happens, right? Actually, it does happen. So the band gap decreases with electric screening, but it decreases even more at the metal contacts because essentially the metal contact is just kind of like having an infinite K over here. So you can see that's going to be the smallest. So this is great. It's great for making lateral band gap engineering, which is what these papers claim, right? But it's definitely something we have to keep in mind for electronic devices, which is something that this is only something I learned in the last year or so, and I've always often wondered what the hell's happening in our transistors. Okay, number 6, band gaps are a function of strain. Again, this is a little, I think is partially known. I think it's not that well studied, and we see this in our samples actually, but it's a big deal because what happens is, okay, you have direct band gap with no strain. Fine, I think we all know that. This is MOS2. But calculations show that if you apply, anything more than 1.5, I think, % tensile strain, you're really pushing down the K point, right? You can actually see it here. These are, by the way, 2 separate papers. You're really pushing down the K point. You see this is the direction of strain from compressive, -2.5, to tensile, +2.5. So you're pushing down the K point. You're not affecting the Q point as much. And you can end up with an indirect band gap. Again, big difference, both obviously for optoelectronic applications and for electronics, right? And to go one step further, if you have strain variation across your device, you're going to have basically scattering because this is going to create all kinds of potential ripples in your device, right? So your band gap is no longer nice and smooth as you would like it. In fact, I'm going to dare say that one of the reasons why boron nitride substrates work so well is they're ultra flat. They don't induce local strains, and therefore, they don't create these sort of like potential ripples that, other things that have roughness induce. There are actually some papers, which I'm not citing here, that have correlated transport properties with surface roughness, and I'm willing to buy it's due to strain. Minor stuff. This is, again, the Celsius versus Fahrenheit stuff. It's not a big deal. But I'll say it anyway because my students told me to say this. By the way, half of these slides were made by my students and half of them were made by me. I don't know if you can, I hope you cannot tell which are which because, I tried to make this uniform. So what my students tell me, okay, this one was my students, not me. What my students tell me is that the correct labels for the Raman modes of MOS2 are E prime and A1 prime. And this notation, which I see very often for monolayers, is actually really for bulk. And oh, and by the way, for even number layers, because these belong to different point groups. I don't know almost anything about group theory, but people who do tell me that this is correct, like that. And then the other thing that the students told me is that WSE2 is a little bit more special too, because it has a degenerate peak, that's these two together, and then this little bump over here is actually twice the LA mode, the longitudinal acoustic mode along the M direction. So kind of a minor thing. The silicon peak, by the way, is just shown there for reference, just to kind of see where these things are when we take measurements. So again, I don't think it's a big deal if people call these things differently, as long as you know what they're referring to. So this is a really minor one. Okay, this is a busy slide. This was actually prepared by one of my students who does growth, I'll tell you that. And I really tried to clean it up, but I left a lot of things in. This is about growth. So I'm switching, by the way, from basic materials complaints to growth now, and then to devices. So there's not really an alternative fact here. I think maybe if there is an alternative fact, is maybe because I get this question sometimes, it's, are your CVD grown materials as good as the exfoliated stuff? And the answer is, it depends. I mean, I don't know. That's not necessarily an alternative fact. It's just a question that I get sometimes. So, just kind of looking at this, mechanical exfoliation, of course, we all love it because it's very easy. You get pretty good electrical quality most of the time, but anybody in industry that I talk to, they don't want to hear about it, right? If I mention mechanical exfoliation to any of my sponsors, they will take away my funding, right? So, so I can't do this really, except rarely. But we do this in my group. We do solid source CVD, which it's great. We can make these Stanford logos on a centimeter, like a postage stamp thing. It's pretty cute. It's fast and easy that even electrical engineers can do this. The electrical quality is pretty comparable actually for us, at least for MOS2. But here's the problem: the temperature is high, and the quality varies from week to week. So yeah, that's a problem. That's a real problem. Okay, so now moving on to, I'm grouping these together, MOCVD and ALD. So these have, these are sort of like, there's shower heads. Notice it actually literally says shower head. Shower heads, of stuff. There's liquid sources. There's really weird chemicals in here. I'm not a chemist, so to me this sounds like really toxic and awful. But apparently, this is much more reproducible and uniform. So my group doesn't do this, but other groups have done it. It's much more reproducible and uniform. It is industry friendly. All my industry sponsors are saying, quickly move from this to this, because this is what they want in their, fabrication tools. And I think the temperature could be lowered a little bit more. The electrical quality here is not that good yet. I haven't seen good electrical data from MOCVD or ALD grown materials, at least not as good as our data from the CVD grown stuff. And that's partly, usually because the grains are quite small. And my students and my staff tell me that the precursors are kind of slow and toxic, and toxics, and some of them are actually not even allowed at my university. So, to be determined. MBE, simpler reactions, easier to make alloys, low temperature, fine. Same problem electrically. We haven't seen good electrical data. That's kind of why, and it's slow and expensive. So industry doesn't like MBE unless they really, really have to. So industry would really like to be here, ALD or MOCVD, and they'll start using this stuff tomorrow. So if you work on growth, I think this is really, really important. Okay. Strain. Maybe I should. You can see this is a rough draft or a rougher presentation. I really should have moved this strain slide earlier when I talked about strain already. But this is strain from growth, so I put it with my growth slides. I think for many years, for several years, my students and I were not really aware of the fact that when you grow these things directly on SiO2 or whatever the heck we grow them on, there's actually a significant amount of strain built into our samples, because the MOS, whatever the material is, in this case, I don't know, this picture says WSE2, it has a different coefficient of thermal expansion than the substrate, right? So again, it sounds very obvious in hindsight, but we just weren't aware of it. because we were silly electrical engineers focused on just electrical measurements and then wondering why there's so much variability in our measurements. And so there's this nice work by Ali Javi a couple of years ago, Nature Communications, basically showing how they tuned the strain by playing with the substrate. So this is SiO2, aluminum nitride, STO, blah, 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 different substrates. And by playing with well, actually, this is still the substrate. This is actually showing the strain amount as a function of the thermal coefficient of expansion mismatch between the WSC2 and the substrate, right? If they're matched, like it is with sapphire, then apparently you get no strain on sapphire, they claim. And I believe it. But on SiO2, you can actually get up to almost 1% strain, tensile strain, because SiO2 doesn't really thermally expand nearly as much as WSC2. So they claim that you can strain tune from compressive to 1% tensile, and you can strain tune by about this much simply by playing with your growth temperature. And I totally believe this because we're very definitely matching these predictions. These measurements in our lab right now. So I think this is really something we have to be aware of going forward. I said growing forward, that too. Growing or going forward. This is something I became aware of when my student Michael Mletzko, former student because now he works at Intel, when my student Michael Mletzko started working on the tellurides. Notice that my earlier question was about tellurium vacancies because tellurides are a nightmare. So then Michael, read what was available in the literature. This was 2015. Somebody showed, hey, look, if you leave molybdenum in air, it disappears. It doesn't disappear right away, but it disappears over about a week. Monolayer is definitely gone. And so he prepared this cute table, which is obviously very qualitative, showing these are like the most stable TMDs, MOS2, and then these are like as you go this way, as the chalcogen gets bigger or the metal gets weirder. The stability is worse, right? And again, I'm not being a chemist. This is made a little bit by, experience and by what we've seen in the literature. So please take this, not that seriously. But I think you'll agree with me that moly sulfide is, much more stable than any of the tellurides, for example, and selenides. So this is another thing that Michael prepared. He basically said, look, these three materials are the most prevalent because they're the most stable. Our students, I think, know that. As a professor, sometimes we don't know that because we're not the ones doing the experiments, but the students know that, and the students want to graduate, and they don't want to work with black phosphorus in my lab. So, of course, you can work with some of these things if you work in glove boxes, but again, some students are better with glove boxes. Our glove box is not particularly great. It is what it is. It's good enough to make the tellurides work. Or we cap them to make them more workable with either ALD aluminum oxide, or we cap them with HBN inside the glove box, and then we can actually do electrical measurements, and the data doesn't look completely like junk. So yeah, so what I was actually writing here is this is to borrow a phrase from Al Gore, another former MIT. Did I say MIT? I was reading MIT News today. Another U.S. presidential wannabe, Al Gore, was referring to our neglect of climate change as an inconvenient truth. So that's more of an inconvenient truth than an alternative fact. This is probably more of an alternative fact. I go to a lot of conferences where people say, I made gold contacts, but they really mean they made Thai gold contacts. And there's a big, big difference. Titanium reacts with these things. Titanium reacts with oxygen. It reacts with sulfur in the MOS2. And so basically, I'm going to come out and say it that if you're ever using a titanium sticking layer to your contact, what you actually have is a Thai oxide or a Thai sulfide contact. And there's much, much work by Bob Wallace at UT Dallas going back now at least 3 years, showing that, showing how this happens. He's done lots of XPS. He's done lots of elemental analysis. This is actually a more recent paper on archive from Andre McCoyan from University of Minnesota. He doesn't see the oxygens here, but he definitely sees the titanium eating. It's literally eating away the MOS2. So the MOS2, even calculations show that titanium just goes and eats at the MOS2. Of course, gold and indium, by the way, they don't react. Is that good or bad? TBD, to be determined. Silver, horrible. Silver will eat your molybdenum, but scandium will also eat your molybdenite, by the way. But here's what we did. This is actually from our recent work. This was just published a couple of months ago. If you can work with a really crazy metal like scandium, but you have to put a really thin layer of boron nitride in there. So we made contacts with scandium metal, one layer of boron nitride, and then the molybdenite, and that's the only way to get the right work function in there. Because luckily the scandium does not eat the boron nitride. Scandium just wants to eat the molybdenite. So again, not being a chemist, to me this is a little bit of magic, but when I talk to real chemists, they tell me this is actually not magic, it's real. So I know this is kind of difficult to read, and I apologize. I kind of group things by what we've learned happens. So Ti is really bad for contacts. Chromium probably next bad. Iridium oxidizes too. I should probably order them. Yttrium and scandium are probably worse than iridium, but iridium has been shown to eat sulfur. You see, iridium sulfide is formed in these contacts. As far as I know, gold, indium, palladium, nickel, and aluminum don't react with MOS2 at least, but nickel and aluminum oxidize, especially aluminum. Aluminum oxide we've used as for gate dielectrics. Aluminum is just really happily oxidizing, but it doesn't seem to eat the sulfur. Silver and scandium, forget about it. You really need to use basically, protective boron nitride layers if you want to do anything with the contacts. Then Professor Bob Wallace tells me that palladium, iridium, and chromium actually react with tungsten selenide. So there's a difference, right? They don't react with sulfide, but they react with tungsten selenide. Again, another, sort of indication, as I may have said earlier, that the selenides are more reactive. So, if you don't agree with that, then tell Bob Wallace. Tell me, but also tell Bob. Also, by the way, if you are working with monolayers and you use titanium or any of these reactive metals, it's going to eat your monolayer. So you may be forming edge contacts and not realizing it. My point is that contacts to monolayer are not the same as contacts to multilayer. If you have a multilayer, like 3, 4, 5 layers, then you're probably only going to eat the top layer, and you might be fine with the rest. But if you're working with monolayers, and you're using reactive metals, then you're going to have a problem. Okay. So I read lots of papers that say, I've discovered a new 2D material, and the mobility is high. Please, nature, please accept my work. And very often, this does get accepted in nature. And then I go, okay, what is high, right? What is high? And this is all at room temperature. I'm not doing any funny business with million mobility at low temperature, right? What is high? So here's my plot of what is high. So indium antimonide at room temperature is about 30,000. Gallium arsenide at room temperature is almost 10,000. By the way, indium arsenide is up there too. I just didn't put it because it's the same. Germanium at room temperature, these are electrons, these are whole mobilities. So these are bulk materials. Indium antimonide, again, 30,000. Gallium arsenide, 9,000. Germanium, it's almost 2,000. Silicon is, depending on if it's bulk or surface mobility, it's still about 1,000 or a little bit less than 1,000, right? So then I read these papers saying, I created a black phosphorus transistor with mobility of 1,000. It's high mobility. And I go, no, it's not, right? I think this is completely fake news. Because, and not only that, but this particular work, which I'm not citing here, was actually done on 10 nanometer thick black phosphorus. 10 nanometer thick, pick any of these, and you have better mobility. So I don't see a point on 10 nanometer thick black phosphorus. The other thing is that some of the, and I'll come back to this, some of the, mobility measurements are incorrect. So again, another very famous paper said mobility of MOS2 in monolayers is 200, but then there was a correction to that paper, which I am citing here, that said actually it was 7. That's a problem, right? But a lot of us believed it was 200, and then when we went to the lab, our students said, but Eric, I cannot get 200. And I said, you're wrong. That paper says it's 200, right? And then the student said, no, I think the paper's wrong. And of course, the student was right. But we didn't know why until we read this Nature Nano, paper. Actually, the student, sometimes they don't say they're wrong. Sometimes they just say, I got to try again. So that's what I mean. This actually wastes time in my lab. The thing is that mobility really is not just a number. It really has to be compared at the same temperature and the same carrier density, and preferably at the same thickness, right? So it's not fair to compare the mobility of, monolayer materials with the mobility of bulk materials, because bulk materials, as I showed yesterday already, if you make them thin, the mobility actually comes down. quite a bit, right? So if you're going to compare the WSE2, let's say, mobility in monolayers, you probably should compare it to silicon in monolayers. That would be more fair, right? So we have to kind of be careful with that as well. But that's more on us. I don't think that's not bad. It's just maybe we might be selling ourselves short, whereas these papers are obviously overselling the work. This is my students' table of what they believe. My students are very critical of this literature. What they believe is the best published monolayer mobility today, and what the theoretical limits are. And so, I mean, the numbers are, a few tens, maybe 180 if you believe this work in WSE2. And so we're still within a factor of almost 5 to 10 of what the theory probably suggests is correct. Remains to be determined. But certainly this number was obviously not reproduced and ultimately shown to be wrong. So that's a little bit funny. Okay. Number 13. Lucky number 13. A lot of people do two-terminal field effect mobility measurements because they're very easy. But the thing that bothers me is that, so they do the two-terminal field effect mobility measurement. There's a backgate here, of course. And then what they say, I measure the mobility to be, I don't know, 40. But it's probably an underestimate because I didn't de-embed the contacts. And so I'm actually here to say that it actually may be an overestimate, right? And people are just starting to realize that. In fact, there's a really nice paper by Professor Saptarshi Das at Penn State. This came out 2 months ago. Thank God people are saying this. But you notice that the organic community already knows this. So organic people are ahead of us by a few years. They have their own problems, their own fake news to deal with. But we're finally waking up to our own fake news, as Professor Das pointed out. So basically what's happening is you have a backgate, and the backgate is gating the contacts at the same time that it's gating the channel. And if you have a Schottky barrier at the contact, you're gating the Schottky barrier. So all of a sudden, and by the way, I believe this is a real experimental data, your transistor, this is current versus gate voltage, it turns on with all kinds of different slopes. And so where you take the slope, where you take the mobility measurement, really matters, right? So what is the mobility in that case? Of course, people who publish this kind of data, they will always take the peak slope and say that's the peak mobility, right? This is also taken from one of the organic literature papers. I think this is just normalized to 1, so I think this number doesn't have units, it's just normalized to 1. So 1 would be the real mobility, and they showed that if you have really strong, Schottky barriers, the contacts, you can really overestimate the mobility by a factor of, like, they say 3 here, but there's this other paper that says a factor of 10. So it depends on the contact resistance. And if you have a small Schottky barrier, but you still have contact resistance, of course you are actually going to underestimate it. But actually most people are in this regime, so they're probably reporting mobilities that are too high when they do field effect measurements. And so, I don't really trust that data. Oh, my comment here, I put it in bold because I wanted to say this. If you extract the mobility measurement, and I'll show this on the next slide, you need to be able to take that mobility number, 40 or whatever it is, plug it back into the transistor equations, and actually replicate the full IV curve. If you can do that, then your data is good. Your extraction is good. If you cannot do that, then you probably made a mistake somewhere. But almost nobody does that. Almost nobody goes back and plugs the mobility they extracted back into the IV curves to show that they can replicate the IV curves using a simple, textbook transistor model. Okay. So this is my attempt at doing that. Maybe it's not the best way to represent this data, but I'm telling you, I really struggled with this. I made this slide myself, and I was kind of struggling how to show the data. In the end, what I decided to do is to show current as a function of channel length. This is a scary large number of channel lengths. This goes from 7, 8 nanometer channel lengths all the way up to 8 microns. So it's over 3 orders of magnitude. This is data from the literature. The blue is data from the literature. The red data is data that we actually have in my group right now. So we've made lots and lots of really short channel devices. And so this is the saturation current, the maximum current measured as a function of length at, and I think I wrote this is at a very specific voltage to compare apples to apples, 1 volt across the source and drain. 1 volt across the source and drain, just to make things easy to compare. Otherwise, it's just very difficult to compare things. This is my simple model. I think everyone is able, everybody with a pocket calculator, Excel, MATLAB, whatever, can use a model like that. This is really, really simple. But it includes, carrier density, mobility, drain voltage, and the contact resistance, okay? And so these are the lines of that model with a few assumptions. So mobility of 40, fine. And then contact resistance of 1 kilomicron, 2.5 kilomicrons, 10 kilomicrons, just to kind of show, what it looks like. And then I'm zooming in. Okay, you can say, fine, this is really difficult. It's really messy. Forget about it. But I think everybody can make devices between 1 micron and 10 micron, just using, Scotch tape and optical lithography. And this is what the current should look like. If I pick the middle curve and with 2.5 kilomicron contacts, if you have mobility of 100, of 40, of 10, you should be getting current levels of whatever this is, 20, 80, or 120 microamps per micron of width. If you are not getting those current levels, then your mobility is probably not this number, and your contact resistance is probably not that number. So it's just good to check your extraction and plug it back in. Oh, by the way, when I plotted these lines right here, I was using a carrier density of 2.2 times 10 to the 13 per square centimeter, which is about the highest carrier density that we can electrostatically gate in these materials. This is 1 volt across a nanometer of SiO2. Of course, our devices don't have a nanometer of SiO2. They have, 10 nanometers of SiO2, so our gate voltage are more like 10 volts. But I'm using this simple number because it's just easier to scale. So if you happen to have 100 nanometers of SiO2, this means a gate voltage minus threshold voltage of 100 volts. And then if you don't get exactly that, just adjust it. We have a website called 2d.stanford.edu, which actually my students, actually I'm not sure if I'm showing that website. Whoops, maybe I should just tell you. We have a website called 2d.stanford.edu, maybe it's one of my later slides, that has all this data already and data from the literature, and we're probably missing stuff, but please tell us. Okay. Another problem is that I read papers that say, please nature, please accept my paper because I have really, really steep turn on of my transistor. And so my postdoc, Alvin Dowse, actually told me, he said, it's possible to get even below 60 millivolt per decade turn on if you have the right amount of charge trapped in the dielectric. And I thought, oh, that makes sense. How come people don't talk about this? And he said, well, they do, but it's in the other literature that the 2D people, the 2D community doesn't read. Okay, so there's so many papers that we've read that have amazingly steep turn on, 70 millivolts per decade, Nature, Science, right? And my postdoc says it's probably due to charge trapping in the dielectric. They probably didn't check their hysteresis. They probably just published the the steeper looking curve, and that he's very suspicious too. I'm telling you, my students are way tougher than I am. And so he says, Alvin, my postdoc, actually says, you have to sweep the voltage, the IV curve back and forth, look at both sweep directions, and you probably should look at the sweep rate as well, because it's really possible, depending on, this is depending on the sweep direction, forward, reverse, sweep direction, you can get different mobility, and you can get different subthreshold slope, and occasionally you can get sub 60 millivolt per decade subthreshold slope, which shouldn't be happening at room temperature, not in a MOSFET. This is not a tunnel FET. If it's a tunnel FET, fine, that's a different animal. But these are MOSFETs, right? And so, for that, by the way, we've done pulse measurements to get around this. So here we show that mobility actually converges to a constant value if you use, millisecond pulses. But if you use DC measurements and you try to extract the mobility from the reverse or the forward, sweep, you actually get different numbers. So that's clearly dependent on charge trapping and a sweep direction and all that. Okay. This, now we're coming to probably one of my favorite topics, contact resistance measurements. I'm obsessed with contact resistance measurements because we make all these transistors that I showed you earlier that are sub 100 nanometers. And if a transistor is less than 100 nanometers, it's all contacts. Almost all contacts. The mobility almost doesn't matter, actually. I mean, yeah, it should be pretty good, but the contacts are dominating. And so, again, you read lots of papers where people use what's called the transfer length method, TLM. And that's very simple. What the idea is, you measure a number of channel lengths, 1, 2, 3, 4 channel lengths, and you plot the total resistance that you measure as a function of channel length. And you say, what can be simpler? It's true, it's very simple. But, and there's a but, unfortunately. So then what you need to do is you need to extrapolate from the linear fit, extrapolate, and then the extrapolation right here is twice the contact resistance. And you go, great, I got the contact resistance. Look how good it is, right? Well, this is real data from my lab, with real extraction by my students, and they show that if you do this from sufficiently long channels, which are not dominated by the contacts, you get a contact resistance that looks like 250 plus minus 1500. right? So if you're careful with your error bars, that actually tells you that your measurement is not reliable at all, right? In fact, my students tell me that they've even measured negative contact resistance, which, if it's true, they should get a Nobel Prize, right? I mean, you can't imagine how much Intel and Samsung would kill for negative contact resistance, right? It would completely transform all of electronics. Okay, so but you can get that if you're measuring the wrong things. So then what we actually really have to do is we have to include shorter channel lengths, right? So you see, this was what I showed you before, and I'm so proud of this animation. I did this myself. Look at that. Oh, it's so good. Okay. Thank you for enjoying that too. This is including the shorter ones, and then you get a different fit, and now you get 1250 plus minus 500, where I'm still reporting error bars, but check it out. It actually looks like now I trust it a little bit better, because I included these shorter channel lengths, which are partially limited by the contacts, right? So you really need shorter lengths. And then my students also say, this is not the only thing. So I have 3 slides on this topic. This is still topic 15. They say, there's another problem. When you make these things, remember how I said 2D materials have variability? They do. So there's enough variation between the different channels that we really, really have to adjust carefully, and we have to measure it at each threshold voltage. So if I don't adjust for the threshold voltage variation, I don't know if this makes it very clear, but these are the 3 channel lengths, and you have threshold voltage variation when I plot this whole thing. But then, if I adjust it, notice I'm plotting VG minus VT. I'm adjusting for threshold here. So they all now have the same threshold. Then I can measure the resistance at the same carrier density, presumably, right? Hopefully. The other thing that my students also told me is like, look, every device will have slightly different trap charge. So if you have, or doping. So if you have different hysteresis, different defects, different non-uniform doping, you have to either bake your devices to get rid of the hysteresis. You see, this is a device measured in air before. It has this enormous hysteresis. And then after we bake it in vacuum and we measure it in vacuum, the hysteresis is gone. Oh, so we trust the data in vacuum, obviously. So you have to do those kinds of things, or you have to use pulse measurements if you still have hysteresis even in vacuum. Okay, this was prepared by another student in my group, who basically said, there's a funny thing in the literature. People seem to do, there's these reports that report low Schottky barrier. These are Schottky contact barriers, low Schottky barrier. That's the barrier between the metal and the 2D material. So they report low Schottky barrier, but they have pretty bad contact resistance. How's that possible, right? So there's 2 reasons, the 2 ways that's possible. One is their extraction is wrong. That's number 1 reason. So people use this expression to extract the thermionic emission at the Schottky barrier and whatnot. But you can really only use this when thermionic emission dominates over tunneling. And that's not always the case with these 2D contacts. It's just not. So there's a better model, which was proposed by Professor Jörg Appenzeller and the student Penumacha from Purdue a few years ago, which is more of a Landauer transport model, and it includes thermionic and tunneling and even contact gating if you want it. It's just a little bit more complicated to implement. So that actually will give you the correct Schottky barrier. And by the way, the other reason why you might be extracting a low Schottky barrier, even with this one, but having bad contact resistance, is because of what I showed earlier. If you actually stick a boron nitride layer in there, you can depin the Fermi level of your contact, so you can end up with actually a pretty good Schottky barrier. But actually, now you introduced a tunneling layer, so the electrons have to tunnel through that boron nitride. So actually, you still get bad contact resistance. But at least there, we know why, and so there's a trade-off. We're going into that trade-off fully aware that we're fixing one problem and we're breaking another one, causing another one. Oh, another thing that my students wanted me to tell you is that if you look at the contact resistance problem, we probably ought to work on contact doping even more than we work on contact metals. Because the metals, you can only do so much. The Schottky barrier can vary by a factor of probably not even 10 with metals, maybe less than that because of pinning. But boy, you can adjust the doping by a factor of 10 to the 10. That's a big, big difference in doping. So, that's kind of the current thinking in my group, is that we really should be focusing even more on doping than on contact metals. We'll see how that works out. On-off ratio. I go to a lot of talks, I read a lot of papers that say MOS2 or this TMD has high on-off ratio of 10 to the power 8, right? And I go, yeah, it sounds pretty good. 10 to the power 8 sounds pretty good. But actually, if you really look at the best data out there, some of it from my group, the on-off ratio is actually 10 to the 10 published. And in my group right now, we have something like 10 to the 12 unpublished. And I want to put this in context. Again, I want to emphasize that a lot of these measurements are actually limited by instrument leakage. So when they do the measurement, it's actually the instrument that's leaking more than the MOS2 transistor, because the MOS2 transistor is actually pretty damn good. And so, again, to show how this thing works in context, I'm plotting the on current for a bunch of technologies and the off current. And look at this, the on current, fine, it's proportional to mobility, boring. In context, obviously hurt you. But the off current, this is actually really, really beautiful, I think. It clearly scales in with the exponential of the minus of the band gap of the material. So there's your black phosphorus. This is the best black phosphorus data that my students found. It has an off-state current of that much. Indium gallium arsenide is better than black phosphorus yet again, right? So it has higher on current and better off current. Polysilicon and silicon are yet better. This is polysilicon. This is stuff that's in our displays and whatnot, keeping our displays black. And this is MOS2. The off-state current is better than silicon. Finally, we're better at something, right? The off-state current is actually better than silicon. Fantastic. But then, before I get too happy about that, then my Japanese colleagues tell me, wait a second, actually IGZO, indium gallium zinc oxide, has a off-state current that is so low that it's almost impossible to measure, but they've measured it somehow, because it has a band gap of 3 eV. So if you want really low off-state current, you actually probably should be working, or we should be working on IGZO. So the on-off ratio is actually better than 10 to the 8th, but it's worse than IGZO. It's a lot better than, obviously, some of these other materials. Okay. This is benchmarking. This is more of an inconvenient truth. I pulled this directly from the IEEE run International Roadmap for Device and Systems. So this is all what they think silicon technology needs to look like starting now and going into the future. And here's news, the bad news. The inconvenient truth is that there's absolutely no 2D transistors today which are better than silicon, except maybe in the off-state current. That's what I showed you earlier. So the on-state current almost meets the benchmark, but not quite. The I-off, okay, maybe I should put this in bold. The I-off is better because we have a bigger band gap, but that's sort of obvious in hindsight. But our contacts, our voltages, our threshold voltage, oh my God, they're not good. They're not good. So this is really what we're aiming for if we want to be taken seriously, is really trying to go after what industry agrees on we need to be going after. Okay, this is what I was going to show you earlier. I mentioned this website already. 2d.stanford.edu is a website that my students put up that basically has all their spreadsheets. We just took all the spreadsheets, we put them in the website, we put them online, and we plotted them, and then you can play this in JavaScript. You can play with all kinds of plotting, and I'm sure we're missing lots of papers, so just click the button right there that says Submit Paper, and that's going to come to us, and then we'll update this with the data that we're missing. I think I have, I can't see my my timer there because some alert popped up. But one other little thing about transistors, and I'm almost done, is that, again, if you work on transistors, this is kind of a big deal. If not, it's not a big deal. But I work on transistors, so I have to watch out. A lot of people say, a transistor, when you make it really short, it has to be 3 times this electrostatic scaling length, and they cite this figure. This, by the way, is from all the electronics textbooks. Yes, sir. Oh, okay. So 5 or 10? Okay, thank you. I can stop right here because I'm almost at the end. So finish? Okay, I think I have 5 slides, or maybe 3. Okay, thank you. All right. We're looking at the electrostatic scaling length here, and so this from textbooks turns out it doesn't apply to 2D transistors. And we just realized that very recently we just submitted a paper that includes this. And so I'm not going to go through the boring details, but the boring details are that for every transistor until today, these transistors, the oxide thickness has always been thinner than the channel thickness, right? Channel thickness for silicon is like 10 nanometers or something like that, and the oxide thickness is 2 nanometers. So this equation applies just fine. But we're in the opposite regime. Our transistors have, 3-atom thickness. So our oxides are always, always thicker. So we actually find out that equation is no longer good. We derived another equation. It turns out to be simpler. We backed it up with all kinds of simulations. And the explanation for that is that most of the electric field actually travels in the oxide right now than inside the semiconductor, because the oxide has become thicker. Okay. I think I have 2 comments on thermal properties. One is on measurements. The other one's on experiments. Measurements. The other one's on simulations. Again, this is courtesy of my students. So there's 2 different things. One is optical methods. In the optical methods, you really need to know your optical absorption. If you're doing Raman, if you're doing optical absorption measurements, if you're doing, usually Raman is what people use. If you don't know your optical absorption, especially as a function of temperature, you're going to publish stuff like the graphene thermal conductivity is 5,000, which we now know is actually incorrect, as was discussed yesterday. The true number is probably a factor of 2 to 3 lower for non-isotopically pure suspended graphene. And then there's another paper, which this bothered me a little bit more because this is actually an unphysically low number. They got a thermal boundary conductance between the MOS2 and the SiO2 of 1 megawatt per meter square per Kelvin. And it turns out that would be a world record. That really should be a Nature paper, but it was actually published in a pretty small journal and then followed up by other groups. And if you read the paper, they just didn't do the optical absorption calibration. The other thing, which is maybe a little bit more pedantic and a little bit more minor, is that a lot of papers say, my device is on a big, thick silicon wafer. So the silicon wafer must be at room temperature. Wrong. It turns out, we've done these measurements because the Raman laser actually goes through and you could directly measure the silicon surface temperature. It turns out during these thermal measurements, actually the silicon substrate also gets warm. And it's the surface of the silicon wafer that gets warm, and of course the rest of the silicon wafer temperature kind of drops eventually. But there's a correction. The correction's probably 20%, maybe more, maybe even 20 to 30%. It's actually a pretty large correction. But it's not as large as 10 to 20x. That's crazy. That's just optical absorption garbage. Modeling. Okay, my student does modeling and molecular dynamics modeling, and he tells me a lot of MD papers that he reads, they use interatomic potentials that are fit to only harmonic properties, like the dispersion relation, the phonon dispersion relation. And he says, yeah, if you did that in a harmonic crystal, you would have infinite thermal conductivity, and that's not right. So you really need to include the unharmonic effects correctly to get the realistic thermal properties. And so some of the molecular dynamics potentials which are out in the literature are unfortunately incorrect. And of course, if you just copy them, you're going to also get incorrect results. And unfortunately, this error has been propagating for a while in the literature. I'm not an expert in MD, my student is, and so I obviously just make sure I'm passing this on. This, I think I showed yesterday. This is my Avengers and my presidential candidate slide. This is really just me saying, again, I thought it would be fun to sort of end on this slide, but it's really just saying that, sometimes in this community it feels like the 2D materials are just graphene and MOS2, right? Somebody asked me recently, like, why does the whole community publish on MOS2? And I said, well, because it seems to be air stable. That's probably why. But there's actually more than 1,000 2D materials that have been, at least suggested. And so my message to the sponsors, which I also made yesterday, is that the field is actually really huge. And my thinking is in the US right now, we're actually underfunded because the sponsors think, oh, it's just like nanotubes. Nothing's going to come out of it, right? And so they say, well, let's just give them a little bit of money and then move on to the next hot thing, whatever that is. But it's not like carbon nanotubes. It's not even like graphene. This is actually 1,000 times bigger than nanotubes and graphene. And I think we're getting 1,000 times not enough funding. And I'm sure you feel the same if you, So here's who helped me with the work. These are the students who actively send me slides, and the rest, same thing I showed yesterday. Thank you very much for your time. Yes. Any questions? Tell me what's wrong. Yeah. Right.